spent some time looking at searching algorithms, but now we're crossing over into new territory: algorithmic design strategies. To solve a massive, seemingly impossible computational problem, you have to refuse to solve it all at once. Instead, you split it into smaller, manageable pieces. For centuries, the math world operated under a strict speed limit. To multiply two large numbers together, everyone used the standard digit-by-digit method we learn in school. As the numbers grew, the time it took to calculate them squared. This was the n-squared barrier, and it was considered an unbreakable law of nature. In 1960, the eminent Soviet mathematician Andrei Kolmogorov held a seminar at Moscow State University. He stated this n-squared limit out loud as an absolute proven fact. Sitting in the audience was a 23-year-old student named Anatoly Karatsev. He heard Kolmogorov's absolute limit, and he decided to challenge it. Within a single week, Karatsev returned with an answer. He realized that by splitting the large numbers in half and feeding them back into his formula recursively, he could bypass the traditional multiplication entirely. The method was subquadratic. It bypassed the speed limit. When Kolmogorov saw the proof, he was so thrilled to be wrong that he immediately communicated the result to the academy and terminated his own seminar. The central open problem was solved, all through the logic of dividing the math. Karatsev's breakthrough is a textbook example of a three-step operational philosophy. First, you divide the data into smaller pieces. Second, you conquer those pieces, usually by applying the exact same function recursively. And third, you combine the partial results back together to get your final answer. For this to actually save you time, there is one mandatory requirement. The broken-down subproblems must be completely independent from one another. Because the individual pieces don't share overlapping work or rely on each other to finish, they can be calculated simultaneously. In a modern computer, that means you can hand different pieces to completely separate processing cores. You can see this clearly on a standard array. The initial list of numbers splits downward into trivial base cases, gets solved, and then merges upward into a single sorted list. Karatsev multiplied 12 by 34 by splitting them in half. While standard math needs 4 multiplications, Karatsev used an algebraic trick, reusing values to compute the middle term with only 3 products. Recombining yields 408. Skipping one calculation permanently accelerates massive computing speeds. We measure this with the master theorem. Balanced algorithms like merge sort match split and processing time, fitting case 2 for an n log n runtime. But Karatsev shrinks faster than its dividing overhead. This pushes it into case 1, producing the shocking subquadratic runtime. The math from 1960 is the backbone of the modern internet. Today's massive datasets are far too large for any single machine to process. To handle this data, modern distributed frameworks like Apache Spark run literal divide and conquer code. When you call a command like parallelize, you're explicitly executing the divide step. The system cuts the massive data pool into tiny partitions and ships them out to separate CPU cores. From there, the map function takes over to conquer independent partitions in parallel. Finally, the reduced function kicks in to combine scattered partial results. This map-reduce cycle powers the cloud giants of our era. It is simply a 60-year-old algorithmic strategy operating at a planetary scale. Whether it's sorting a database with Quicksort, looking up a record with binary search, or crunching petabytes of user data across AWS, the split and solve approach is everywhere. But there is a boundary condition. If your smaller subproblems overlap and you find yourself computing the exact same shared work multiple times, the efficiency collapses. That gives us a definitive rule for developers. If your pieces are completely independent, divide and conquer will win every time. If they share work, you need to step back and use dynamic programming instead. The exact mechanics of these strategies and the code to run them are outlined in 50 algorithms every programmer should know. Next time, we're going to look at an algorithm that ignores the big picture completely, surviving by making the most selfish, greedy choice at every single step.